Hey, what's up? It's your old pal, Mr. Cook. We're going to go through this Unit 7, Part 2 test review. We already went through the first 10 problems, so now we're going to, start at 11 and see what to do from there. So let's see. It looks like 11 through 13, we have to determine the degree for the Maclaurin polynomial centered at 0. Required to approximate that for sine of x with an error less than 0.0002. Okay, so for this one, basically just use like the idea of calculating error. Let's see here. So from here, the idea is that Taylor's theorem, well, we don't really have like the rule for error on that page or that one. Okay, well, I guess we don't have it on the little formula sheet. So you just got to know that like the error amount that you're going to have, either if you're using alternating series test and the error for alternating series, or if you're using for a Taylor expansion, it's going to be the first neglected term. That's going to be your max, the maximum amount of error that you can have. And the idea of it comes from this, like if it's alternating, and I'll just kind of briefly describe what's going on. If you have like an alternating series and if you're taking partial sums, like so maybe you only take the first term and add it up, so it's just one term, or the second term, two terms and add it up, or if you add up three terms, or if you add up four terms of the summation. The idea is like you want to get to a point where you're at like like infinitely many terms, okay? And if it's an alternating series, so I'll go over like the alternating series version of this because I think it's a little easier to digest. You get some first term, and it could be positive or negative number. It doesn't matter. I'll just make it positive arbitrarily. So if I add up just the first term, that's all that this is going to be. The summation of partial sum is just going to be the very first term, and that's it. The partial sum with two terms would add up the first term and the second term. Okay, and in an alternating series, that means that one of them is going to be positive and one of them is going to be negative. So what happens to this number right here is that it like goes down a little bit. Like so, because if this is positive, then the next number added on will be negative. So it'd go down by some amount, like maybe down to here or something. And then that would be your partial sum for two terms. And then for three terms, the partial sum for three would be the first term, which is positive, the second term, which then would be negative, and then the next term would be positive after that because it's alternating. So then it would add some amount on. So this amount would go up by a little bit, but not as much as it got to like when it was over here. Okay, so it'll go up like kind of in between there, like maybe like right there if you add up three terms. Okay, and then you keep doing this pattern. So S4 would then be negative. So if you add up all four of the first terms, that would give you S4, and it'd be a little bit smaller than that, like maybe down to here. And then at the infinitely many term, you're adding up all of these terms together. Okay, so all of them together, and they're a bunch of alternating values, and they get to some number. Okay, and that number, interestingly enough, is going to be like, because if you keep going like up by some amount, like at the first term, and then you go down and up and down and up and down, it's going to be centered around like one single value. So you notice that like between the first partial sum, the second partial sum, the third partial sum, and fourth partial sum, they all kind of like are narrowing down on one value. So if I just draw a line kind of like in between them, right here ish, it's like close to straight line. Okay, this is going to give you like the amount for the sum. So at the partial sum, at the infinite like many terms, basically, if you add up all infinity many terms, it should get to exactly like that value. Okay, if it converges, if it goes to this single value for summation. What the Taylor approximation and what the Taylor error and the alternating series error basically kind of create is this. All right, so like let's like count one value in green as the difference between the the actual partial sum, the partial sum that you're looking at, like S1, and the actual value that this approaches. In other words, like the limit of the partial sum. And then all these little green values, what we're going to call the error, okay, the true error. Okay, so it's like the distance between the partial sum and the actual real summation that you're going to get. Okay, so all these green ones are error, actual real error. Then if you look at, how far the partial sum has to go from one term to the next, so just like the distance from like this one to this one, if I go that distance, it's like something like this. So I go down like that much to get to the next point. Okay, so I'll call this blue amount like the difference between partial sums, or I'll call them S's. S, we'll call it N and Sn plus 1. So one partial sum and then its next partial sum. So the way that I calculate that each time is like by checking the distance between the heights of two partial sums, and then drawing that amount up. I'm a little high there. There we go. And then this one goes from here to here. So it's going to be like this much. And so on. Okay. So then all of these little distances, notice that the blue lines are always greater than the green lines, right? They're like bigger length than the green lines. And this is what we're talking about, okay? The error or the remainder is always going to be less than or equal to, sometimes it's like really close, so equal to the distance between, the first term and the next term. And the way that you find that is just, how do we, go from here to here and here to here and here to here? We just add it on like successive terms. So this first neglected term that you have, the blue amount, is going to be greater than the actual error. So if you want like a maximum amount of error that you can find for any given partial sum, you just look at the next term, okay? That's basically how this ends up working out. Okay, so, there's a little bit of a refresher, and I'm doing that because this idea is a little bit complicated, right? So, but luckily, it's formatted basically the same way every time. You need to find like the degree of a polynomial, of a Maclaurin or Taylor polynomial, and find some amount of error, okay? So this is going to be like our threshold. That's like the upper bound amount, okay? So that's going to be like the biggest difference that we can get. And when you read this question out, determine the degree of the Maclaurin polynomial centered at 0, required to approximate f of 0.4 for the function f of x equals sine of x for the error to be less than that much. We'll notice that like it's formatted the same way for these 3 problems in a row. That means that you're just going to be doing the same steps. And here's how the steps work. So if you just want procedurally what to do, here's what you do. You just need to translate this into a Maclaurin polynomial. Okay, so use the either the rules that we have, the power series list of rules, or the Taylor pattern. And then what you do is from there, you just list off terms and you plug in 0.4 for your x value until the terms get smaller than 0.002. Once they do, that's your cutoff, and you just put a partial sum up to that amount. So here's how it goes. Ready? You take the function f of x equals sine of x, and then you convert it into a power series. And the power series for sine is n equals 0 to infinity of -1 to the power of n, and then x to the power of 2n plus 1 over 2n plus 1 factorial. Okay. And where did I get that from? I have it memorized, but you can just get it from your little formula sheet that you're going to have on the test. See, it's right over here. Or is it sine? Right there. Okay. I know it's a little pixelated, but you'll get a fresh copy that doesn't look all pixelated like mine does. But yeah, that's the pattern that we're going to use. And so we just need to list off a couple of terms, and then we need to plug in 0.4 and see when it finally gets to 0.002. Since this is the method to solve this, usually Mr. Felling and I, or when we put together a test, in general, we don't tend to make you do a bunch of terms as a result, 40 terms or something. So usually if you do 4 or 5 terms to check them out, that's usually good enough. Okay, so yeah, let's start plugging in, 0 and all that to get the pattern down. So I plug in 0, I get -1 to the 0, and then x to the 0 plus 1, which is 1, over 0 plus 1 factorial, so 1 factorial. And then plus, and then I've got -1 to the second power, and then x to the, let's see, so this will be the first term. 1 times 2 is 3, 3 plus 1 is, 1 times 2 is 2, 2 plus 1 is 3, so that's going to be to the third power over 3 factorial. And do you see the pattern that's already forming here? Yeah, for the next one, we're going to have -1 to the third power, and then it's going to be x to the fifth over 5 factorial, and then -1 to the fourth power, x to the seventh power over 7 factorial. So it's always going to be the odd numbers, and then -1 to the fifth power, x to the 9th power over 9 factorial. And that's 1, 2, 3, 4, 5 terms. I could keep going if I wanted to, okay? But I'm going to try my luck and see if plugging in 0.4 and using my calculator yields like a number that's like small enough, less than, you know, this amount, 0.002. So that's going to be my cutoff. I need to make sure that the term that I get is smaller than that. So once I hit that number, smaller than 0.002, 0002, I'm sorry, then I'm just going to stop, okay? So next I'm going to plug in 0.4 for all of these. So -1 to the 0, which is 1, times 0.4 over 1 factorial. That's just, I mean, I'm just going to start simplifying this because I'm going to start, use my calculator in a second. So like, when I'm writing this up, I think to like just minimize as much as I can, because that's less stuff that I have to type in. Like -1 to the second power is just 1. I know that. And then 3, so x is 0.4. So 0.4 to the 3rd power. And 3 factorial, that's going to be 6. I know that one. Okay, and then the next one will be -1. So it's going to be a negative. Actually, I should put a minus on there. There we go. And wait, did I skip a term? Yeah, oops, that should have been a 1. My bad. Sorry about that. So that's a 1. You were probably looking at that the whole time. It's kind of like, oh, come on, Cook, you got to see that one. Yeah, sorry about that. 3, 4, there we go. At least I caught it before I made critical mistakes there. Okay, so so actually this should be a negative number. I'm sorry about that. And then this is going to be a positive, and then it's going to be, let's see here, 0.4 raised to the 5th power over 5 factorial. 5 factorial should be, let's see, 5 times 24, 120. And then let's see here. And then it's going to be a negative number, 0.4 to the 7th power over 7 factorial. Oh gosh, this is really testing me. Let's see. So 6 factorial is 7 for 20. Oh, I'll just use my calculator. What am I doing? I want to save some time. So let's see, 7 factorial. 5,040. And then plus, and then it'll be 0.4 raised to the 9th power over 9 factorial. Oh gosh, 9 factorial. My heavens, let's see. Whoa, that's a big number. 362,880. I do have a feeling that it's going to be way before that one. All right, so let's see. All right, now each term, I'm going to find out what those values are. Okay, so this is 0.4, so that's easy. Let's figure out what that next one is. So 0.4 to the 3rd over 6. So I got 0.0106 repeated. Now remember, I'm looking for a number that is less than 0.0002. I'm not there yet, okay? Now let's get this next one. So 0.4 raised to the 5th power divided by 120. Oh, that's the number, yeah. So I got, it says, here's what it says in my calculator, 8.53 repeating, and then E -5. What that means is that I've got 4 zeros. So 0.1234, and then I've got all these numbers. So 853 repeating, like that. So yeah, this number is way underneath this one. So this is going to be the first neglected term that I have. So I'd cut it off right there, and I would just need the first 2 terms. So what I need is, on the degree of this, it's going to be a degree 3 polynomial because it's x to the 3rd power. So I need a degree 3 polynomial for a good approximation. Okay. Yeah, this is a long video, so I'm just going to stop with this one example, and then I'm just going to go through the next couple like really quick. All right. So yeah, I hope you found this one beneficial for you and like helpful. And but if you didn't, go talk to your calc teacher. If you need my help, I'm Mr. Cook. I'm available in the morning and after school, so just come and find me. All right. Thanks. Hope you found it helpful. I'll see you in the next video. Bye-bye.